Welcome to this session. I am Dr. Y.V.K. Ravikumar. So today we are going to discuss optimal binary search tree as a part of dynamic programming. So already we discussed about dynamic programming. Now, so what is that we are going to do in this optimal binary search tree? So here the problem that what we are going to discuss is so consider a given sequence K which contains the keys K1, K2, so on Kn, which are all sorted keys, where each key is having a search probability Pi. That is, the probability of searching for the key K1 is P1, K2 is P2, and so on. Now, what we need to do is, we want to build a binary search tree where the minimum, where the expected search cost is going to be minimum. That is, so whatever BST that we are going to construct, it is going to give minimum expected search cost. That is the problem which we are going to discuss. So here the actual cost is nothing but the number of items which we are going to examine. And already we are very familiar with this point, that is, for any given ki, the cost that we are going to incur for searching is depth of that ki plus 1, where depth of ki with respect to t is depth of ki in the BST, that is t here. So this is the problem which we are going to discuss. Now what is the, before going for the procedure to find optimal binary search tree, so we'll see how to find or what is the expected search cost. Expected search cost in T is, thus here it contains I equal to 1 to n, where depth of the key ki is given by this depth of ki in the tree T plus 1, because here, so when we search for a key, now we have to go further, that is, we have to increment it by 1, therefore it is depth of ki plus 1 multiplied by its corresponding probability. Then if we simplify this, then what we get this as summation I equal to 1 depth of ki into its corresponding probabilities, that is Pi, plus summation I equal to 1 to n Pi. But here if we say this one, this second term is nothing but P1, P2, P3 and so on Pn, which is nothing but the total probability or sum of the probabilities corresponding to I equal to 1 to n, so that this is going to be 1. This already we are very familiar, that sum of probabilities is 1. Therefore this becomes 1 plus summation I equal to 1 to n depth of ki into Pi. So this is the expression which we use to find expected search cost in T. Now how it works, we'll see with an example. Here consider 5 keys K1, K2, K3, K4, K5, where the corresponding probabilities, such probabilities are given by P1, P2, P3, P4 and P5. So here now, so one approach here, that is one problem we can take as, now taking this K2 as root and constructing the binary tree. So here K2 is at level 0, K1, K4 are at level 1, K3 and K5 are at level 2. Now we can find, now we know I values, we know depth of each and every key, and also we know corresponding probabilities which are given in the problem. So then when I equal to 1, then corresponding probabilities. Similarly, when depth is 0, then probability. When depth equal to 2, then probability. Like this we are having all probabilities. That is, now this gives depth of ki into corresponding probabilities. Then if we sum all these things, then what we are going to get is 1.15. Then by using the previous relation which we discussed, then the total cost that it takes is 1.15 plus 1, which amounts to be 2.15. So this is the, suppose if we with these probabilities, if we construct the binary search tree where taking k2 as the root, then we are getting the search cost as 2.15. Suppose if we go for another combination or another way of constructing binary search tree, that is, now the same 5 keys k1, k2, k3, k4, k5 with the same probability, same problem we are reconstructing, where k2 is at level 0, k1, k5 at 1, k4 at level 2, k3 is level 3. Then in the same way, we can calculate for I equal to 1, 2, 3, 4, 5, that is the number of keys, and next followed by depth of each key. So here depth, now it is 0, 1, 2, 3 here. Then we can calculate the expression depth of key into corresponding probabilities. Then the total amounts to be 1.10. Now the total cost by adding 1 to this will get 2.10 here. Now with the same k1, k2, k3, k4, k5 keys and same p1, p2, p3, p4, p5 probabilities, now we are able to have two binary search trees. This is the previous one which we constructed, where the expected search cost is 2.15 and for the other the expected search cost is 2.10. Now here, so between these two, we want the search cost has to be minimum. Therefore, this binary search tree BST, whatever we constructed, is the optimal one which gives minimum search cost. So like this, for a given combination, we can construct the binary search trees in different ways. So now in this what we are going to do is we have to find a way by using that we can find the construction of binary search tree which gives optimal search cost, that is the minimal search cost. Now between these two examples, if we observe the example 1 and example, that is two binary search trees that we constructed, we can have the following observations. One is the optimal binary search tree may not have the smallest height. That is, if we see the first one as well as the second one here, so this here height is 2, whereas here height is 3, but the binary search tree with the height 3 is optimal. That means it need not be that the optimal binary search tree will have a smallest height. And similarly, it is not necessary that the optimal binary search tree will have the highest probability key at a root. Now, how to do this problem? So one is the regular approach, that is exhaustive checking, or we can apply the brute force search. So by using brute force search, we can construct as many binary search trees as possible by taking various keys or nodes as the root. We can go for various possible binary search trees, from which we'll take the one which gives the optimal search cost, that is minimal search cost. That is what we do when we construct optimal binary search tree by using brute force method or exhaustive search method. So that is what explained here. Construct each node BST. For each assign keys and compute the expected search cost. From that we'll find the optimal binary search tree. So if we use this brute force method, then the complexity is going to be 4 power n by n power 3 by 2. That means here it is going to be exponential complexity. So here, so it gives, if we apply the brute force method, then we are going to have exponential time complexity. Now, so then how to do it? How to construct optimal binary search tree? The first step what we do is we construct optimal substructure, where what we do is, now here we are going to have the keys k1, k2 and so on up to k, that is ki, ki plus 1 so on up to kj. Now what we do is we select one of the keys, that is kr, as the root. So we suppose that this kr is the root of the optimal binary search tree. Then it will have two components, that is it will have left subtree as well as right subtree, where left subtree kr contains ki, so ki plus 1 so on up to kr minus 1. Then the right subtree contains kr plus 1, kr plus 2 so on up to kj. So like this what we do is, so we select one of the keys as a root, then we'll have its a left subtree as well as right subtree. Now how to find optimal BST from this? Then examine all candidate roots kr for given I less than or equal to or less than or equal to j. Then find all optimal binary search trees containing ki plus 1 to so on kr minus 1, and also kr plus 1, kr plus 2 so on up to k. That means now we go further, consider the left subtree. So repeat the same procedure. Now in this left subtree again we'll choose one root here, one root, then again here we'll have a left subtree as well as a right subtree here. So similarly go to the right subtree, choose a key or root here, then again we'll have a left subtree as well as right subtree. Now like this we'll continue dividing the global problem or original problem into sub-problems, sub-sub-problems and sub-problems and so on. Then what is recursive solution? Then we need to find optimal BST for ki plus 1 so on up to kj, where I greater than or equal to 1, j less than or equal to n, and j is greater than or equal to I minus 1. But here when j is equal to I minus 1, the tree becomes empty. Now what we do is we'll find EIJ, that is EIJ stands for here the expected search cost of optimal binary search tree for ki plus 1 so on up to kj here. Now so here we'll try to find the EIJ, that is expected search cost, to find optimal binary search tree for the keys contains ki plus 1 so on up to kj here. So how to do it? If j equal to I minus 1, then obviously the expected search cost is going to be 0. If j is greater than or equal to I, then we have to proceed further, where select a root kr like what we discussed. So select a root kr and recursively find an optimal solution for the left subtree as well as right subtree. That is what we discussed. Select kr, then left side what we'll have is a subtree contains ki plus 1 and so on up to kr minus 1. Right subtree contains kr plus 1, kr plus 2 and so on up to kj here. So now what we have to is recursively we have to find optimal binary search trees for this sub-problem, the left sub-problem and as well as right sub-problem. So we have to continue like this. Now so when optimal subtree becomes a subtree of a node, then depth of every node in optimal subtree goes up by 1. That is already what we discussed. Then expected search cost, that is given by W of ij, that is L equal to 1 to j PL it is. So that is here it involves search cost, that is expected search cost, where we'll search all the keys from I equal to j, that is. Now, so how to have the recursive solution for this one? So here again we see, that is here we had kr as a root, and here we had a subtree, that is from ki and so on up to kr minus 1. This is left subtree, and in right we had a subtree, that is from kr plus 1, kr plus 2, so on up to kj here. Now how to find the optimal cost, search cost for this? If kr is the root of an optimal BST, suppose whatever we have taken, that is kr, this is the optimal BST. So when it becomes optimal binary search tree is, that is now we need to calculate EIJ. So EIJ is, it involves, so first what, so here we have to start the search with the root, that is we have to search first with the root r, that is now this PR is the cost incurred for searching the root r. Next we'll go to the left subtree. So where left subtree contains EI2, that is EI2 r minus 1, that is this EI comma r minus 1 is the cost taken for the search in the left subtree, and this is left optimal binary search tree, and this is W of IR minus 1 is the cost incurred for searching each and every node in this left subtree. And similarly, this ER plus 1, that is here, this is the optimal search cost for right subtree, which contains the nodes KR plus 1, KR plus 2, so on up to J. Then next follows W of R plus 1j. This is the cost taken for searching each and every root in this right subtree. So like this, the EIJ contains the components like, first thing is the cost incurred for searching the root, followed by the optimal cost for the left subtree, and followed by the optimal cost incurred or total cost incurred for searching each and every root or every node in the left subtree, and followed by the optimal cost for the binary search tree, that is right binary search tree, followed by the total cost incurred on the searching each and every node or root in the right subtree. So this is what the expression which we get. Now we can simplify it further, that is if we take the PR and W of IR minus 1, W of R plus 1 and J, these are all nothing but the cost incurred on say going through each and every node, that is including the root as well as nodes in the left subtree as well as nodes in the right subtree. So this we can combine together and we can say that it is W of I comma j. That means here, so finally what we get is the optimal, that is EIJ is, that is the cost incurred on the left subtree, the cost incurred on the right subtree, and as well as the total cost incurred on going through all the nodes in the tree. Here this is what we discussed in terms of KR. Now what we are going to find is we don't know which node or which root gives the optimal subtrees. Therefore what we do is we take the minimum of this, that is then now we'll summarize and we'll say it as E of ij equal to 0 when j equal to I minus. This is already what we discussed. If j equal to I minus 1, then there is no tree. Then otherwise for I less than or equal to j, then we calculate EIJs like this, that is E of I comma r minus 1, E of r plus 1 comma j, and W of I comma j for all possibilities. from which we'll pick the one which is minimum, which gives the optimal binary search tree for the problem which we are looking for. Now, how to find or how to compute an optimal solution? For each subproblem ij, so we are dividing the problem into various subproblems as well as subproblems. Now, what to find the optimal solution? What we have to do is, for each subproblem I comma j, store the expected search cost in a table where it is one to n plus 1 as well as 0 to n. It stores all the expected search costs here, and we'll use only the entries eij where j greater than or equal to I minus 1. Next, if root of I comma j is equal to root of subtree with keys ki plus 1 so on kj for every 1 less than or equal to I less than or equal to j less than or equal to n, then w now we'll find that is w of 1 to n plus 1 0 to n, that is it gives the sum of the probabilities, and also we'll find w of I comma I minus 1 which is 0 where I lies between 1 and n, and w of ij equal to w of I comma j minus 1 plus pj it is nothing but the cost in here. In this case it is j is the root. Now pj is the cost incurred on the root j. So like this we'll compute an optimal solution for the given problem. Then what is its corresponding pseudocode here? Now it contains so first we have to initialize the e as well as w. So that is, first initialize I with 1 to n plus 1 and initialize e as well as w where it is from I to I minus 1 with zeros. Now we have to consider all trees with all the keys, that is for L equal to 1 to n we have to try for all possible trees, therefore that's why it is L is from 1 to n. And first what we have to do is we have to fix the first key, that is here what we are doing here. We have to fix the first key as well as the last key, that is where I is from 1 to n minus L plus 1 whereas j is I plus L minus 1. Suppose L equal to 1, suppose if we take L equal to 1, then it is I is 1 to 0, I is 1 to 0, then j is I minus 1. So j is I minus 1, there is no tree, then e power e comma e of I comma j is 0. That is already what we have seen. Next what we do is we calculate the optimal search cost eij. Suppose now we'll start with eij, we assign some greater value for eij. Then we here taking j as the root, so we calculate wij where it is w of I comma j minus 1 plus pj here. Then what we do is take r assign r I to j, then calculate the optimal search cost for the left tree, subtree as well as the total, that is e of I comma r minus 1, e of r plus 1 comma j plus w of I comma j. Assign this value to t here. Now whenever if t less than eij, so if already eij is we assigned with a greater value, then we calculate eij value. If it is t less than eij, then it concludes and say that e of ij is t, that is it is optimal cost for the subtree which we are constructing. Then whatever the r that we have taken, that is the root of the optimal binary search tree, so that it returns the cost in total cost incurred, that is which is optimal as well as the root here. So like this part explains how to find the root of the optimal subtree, and also it gives the optimal cost incurred on the construction. Now in this case, what is the complexity of the algorithm? Here if you see, here it involves one for loop, that is nested loops here, where if you remember if we recall what we discussed in earlier classes, then the complexity is going to be order of n cube. Thank you.